There is a story about the Moon that most people know. About 4.5 billion years ago, a Mars-sized body struck the young Earth. The collision was violent enough to vaporize rock. A cloud of debris was thrown into orbit. That debris coalesced into the Moon. The story is taught in schools. It appears in every introductory astronomy textbook published in the last 40 years. It is repeated on documentaries, in museum exhibits, and in the first paragraph of nearly every article ever written on the subject. The story has a name. Scientists call it the canonical model. And in 2024, after nearly 5 decades of refinement, the canonical model still cannot explain some of the most basic things we know about the Moon. So why does a consensus built on that model persist in places it no longer belongs? Why have the anomalies, known to researchers for decades, never quite made it to the public version of the story? And what does the Moon actually look like when you stop telling the version everyone agrees on? Monday, October 23, 2023. Jenica Greer, a research associate at the University of Glasgow, publishes a paper in the journal Geochemical Perspectives Letters. She is working with a sample collected by Apollo 17 astronaut Harrison Schmitt on December 11, 1972, a handful of dust scooped from the surface of a valley called Taurus Littrow, roughly 750 kilometers northeast of the Moon's equator. The sample has been sitting in storage for 51 years. What Greer's team does with it is unusual. They sharpen a piece of the lunar dust into a tip finer than a needle, using a focused ion beam, almost like a very precise pencil sharpener, she would later say. Then they fire ultraviolet lasers at the tip, evaporating atoms one at a time. Those atoms travel through a mass spectrometer. How fast they move tells the researchers what they are. The process is called atom probe tomography, and it is the first time it has ever been applied to a lunar sample. What they find pushes the Moon's age back by 40 million years. The previous consensus had the Moon at 4.425 billion years old. Greer's zircon crystal, a microscopic grain invisible to the naked eye, dates to 4.46 billion years. It is the oldest known solid ever recovered from the Moon's surface. And because zircon crystals cannot form until a magma ocean has cooled enough to crystallize, the crystal's age sets a minimum for when the Moon must already have existed as a stable body. It's amazing being able to have proof that the rock you're holding is the oldest bit of the Moon we've found so far, Greer said. It's an anchor point for so many questions about the Earth. This is the character of modern lunar science. Not proclamations, anchors. Small fixed points in an enormous uncertainty. To understand why, you have to go back to 1975. That year, 2 American researchers, William Hartmann at the Planetary Science Institute in Tucson and Donald Davis at the same institution, published a paper proposing that the Moon formed from the debris of a large collision. The idea had floated in various forms before them, but Hartmann and Davis put numbers to it. They calculated the size of the impactor, modelled the energy of the impact, and suggested that the resulting debris cloud could have coalesced into a single large satellite within months, not millions of years. The proposal was initially met with skepticism. However, it had one significant advantage over every other hypothesis at the time. It explained why the Moon is so large relative to Earth, why it lacks a substantial iron core, and why its density is lower than Earth's overall density, but similar to Earth's outer mantle. No other model did all 3 simultaneously. By the 1984 Kona Conference on the Origin of the Moon, a meeting of roughly 100 planetary scientists convened specifically to address the question. A working consensus had formed around the giant impact hypothesis. The impactor was given a name, Theia, after the Greek Titan, who in mythology gave birth to the moon goddess Selene. The canonical model was born. Over the next 4 decades, it would be refined with increasingly powerful computational simulations. N-body models, smoothed particle hydrodynamics, high-resolution impact codes. Each new generation of supercomputers allowed researchers to add detail, to simulate finer particles, to track the composition of debris clouds. to model how quickly a proto-moon could accrete from material in orbit. The picture that emerged was specific. According to the canonical model, Theia was roughly the mass of Mars, about 1/10 of Earth's current mass. It struck the young Earth at an oblique angle, somewhere between 30 and 45 degrees from vertical. The impact was not head-on, but glancing. Most of Theia's iron core sank into Earth's interior. The outer layers of both bodies were thrown into orbit, forming a disk of molten and vaporized rock. Within several months, a single large moon coalesced just outside the Roche limit, the distance at Daipas, at which tidal force would prevent the debris from clumping at roughly 3 to 4 Earth radii from the surface. The precision of these numbers is seductive. It implies a solved problem. However, this is exactly where the canonical model starts to reveal itself. In 2001, a team of geochemists published a finding that should have forced a fundamental revision of the canonical model. It did not. The team analysed oxygen isotope ratios in FAD, lunar rocks returned by the Apollo missions, and compared them with rocks from Earth and with meteorites from various bodies across the solar system. Every body they examined had a distinct isotopic fingerprint, a signature determined by the conditions and location where it formed billions of years ago from the collapsing disk of gas and dust around the young sun. Mars has its own signature. The asteroid Vesta has its own. Even different classes of meteorites from the outer solar system have measurably different signatures. The Moon and Earth had the same one. This is a problem. According to the canonical model, the Moon formed primarily from material ejected by Theia, the impactor. Simulations consistently show that more than 40% of the material in the debris disk comes from Theia's outer layers, not Earth's. If Theia formed in a different part of the solar system than Earth, which it almost certainly did, because every other planet and major body formed in a different part of the solar system, then its isotopic signature should be different from Earth's. The Moon's rocks should look partly alien. They do not. Researchers named this the isotope crisis, not a minor inconsistency, a crisis. It affects not just oxygen isotopes, but titanium, tungsten, chromium, and silicon as well. Each independently analysed, each returning the same result. The Moon is chemically almost indistinguishable from Earth's outer mantle in ways that the canonical model cannot account for. Several solutions were proposed. The most popular was that Theia happened to form in the same region of the solar system as Earth, and therefore happened to have the same isotopic composition. This is possible. It is also, as multiple researchers noted, convenient. It resolves the problem by assuming the problem away. A second proposal, published in various forms through the 2000s, suggested that after the impact, a process of rapid mixing between the proto-Earth and the proto-Moon's debris disk could have homogenized the isotopic compositions. However, the physics of this mixing remains contested. The models that produce sufficient mixing also require impact conditions, angles, velocities, angular momenta, that are difficult to reconcile with the current architecture of the Earth-Moon system. But what makes the isotope crisis even more significant is that it is not the only thing the canonical model cannot explain. The Moon's orbit is tilted roughly 5 degrees relative to Earth's equatorial plane. In a straightforward giant impact scenario, the Moon should orbit much closer to Earth's equatorial plane. The impact would have aligned the two. Getting from the impact geometry to the observed orbit requires additional mechanics that the canonical model does not naturally produce. The angular momentum of the Earth-Moon system is also a constraint. The current system has less angular momentum than most giant impact simulations generate. Explaining how the excess was dissipated through tidal interactions with the Sun, through resonance passages, is possible, but adds complexity that the simple canonical picture does not contain. None of these problems are secret. They appear in peer-reviewed literature. They are discussed at conferences. They are known to every researcher who works on lunar formation. The 2024 review paper by Zhou, Bi, and Liu in Space, Science and Technology states plainly that a range of new computational models depicting the giant impact has been proposed, and no single model has won out. The public version of the story has not caught up. In February 2018, Sarah Stewart, Professor of Earth and Planetary Sciences at the University of California, Davis, published a paper in the Journal of Geophysical Research, Planets that proposed a fundamentally different picture of how the Moon was born. She had been working on it for years. That same year, the MacArthur Foundation gave her a $625,000 fellowship in recognition of the work. Her model begins with the same collision. Theia strikes Earth. However, in Stewart's version, the impact is far more energetic than the canonical scenario, enough to vaporize the majority of both bodies. What results is not a molten planet surrounded by a debris disk. What results is something that had never been described before in planetary science. Stewart and her collaborator Simon Locke, then a graduate student at Harvard, named it a synestia. A synestia is a rapidly spinning mass of molten and vaporized rock in which part of the body is in orbit around itself. The whole structure puffs outward into a shape that resembles, from the outside, a vast flattened donut, a torus of vaporized silicate rock, thousands of kilometers across, rotating faster than any stable planet can. It does not last long, perhaps only a few hundred years. As it radiates heat into space, rock vapor condenses into liquid and the structure contracts. Eventually, it collapses into a molten planet. The Moon, in Stewart's model, forms inside the synestia, not outside it. As the synestia cools, molten droplets condense at its surface and rain inward. Seed fragments from the impact collect these droplets. The proto-moon grows inside the cloud because the cloud itself is composed of thoroughly mixed material from both Earth and Theia, vaporized and homogenized together. The Moon inherits its composition from that shared mixture. It does not inherit Theia's alien signature. It inherits Earth's. The isotope crisis disappears. This is the first model that can match the pattern of the Moon's composition, Stewart said at the time. The Moon is chemically almost the same as the Earth, but with some differences. This new theory helps to explain the previously unexplainable. However, the synestia model is not without its own complications. The impact energies required to produce a synestia are considerably higher than those required by the canonical model. Achieving them requires specific conditions: a faster spinning proto-Earth, a larger or faster impactor, or a more nearly head-on collision, each of which introduces its own constraints. The model also requires that the synestia phase cool quickly enough to form a stable Moon before the structure collapses entirely, which places tight requirements on the timing. And then there is a third model. In 2022, a team running simulations with 100 million particles, one of the highest resolution impact simulations ever performed, found that under certain impact conditions, a Moon mass satellite can form directly and almost immediately from the collision. Not over months, not inside a cooling donut of vaporized rock. Within hours to a day, the Moon snaps into existence nearly fully formed, placed directly into a high orbit far from Earth by the geometry of the impact itself. This model produces a Moon with an outer layer composed of roughly 60% Earth material. It does not fully resolve the isotope crisis, but it gets closer than the canonical model without requiring the extreme conditions of the synestia. 3 models, each solving some problems, none solving all of them, each requiring conditions that the others consider unlikely or constrained. Unfortunately, for the scientists involved, the physical evidence has not stood still while the theorists debate. On November 20th, 2025, a team led by Timo Hopp at the Max Planck Institute for Solar System Research in Göttingen, Germany, published a paper in the journal Science. The title was direct. The moon-forming impactor Theia originated from the inner solar system. For decades, the origin of Theia had been a complete mystery. The canonical model offered no particular constraint on where it came from. Some researchers assumed it formed in the outer solar system and drifted inward. Some assumed it was a co-orbital body, parked in one of Earth's gravitational sweet spots, the L4 or L5 Lagrange points, for hundreds of millions of years before the collision. Nobody knew. Hopp's team used a different approach. They measured iron isotope ratios with precision that had not been achievable a decade earlier. in 15 terrestrial rock samples and 6 lunar samples collected by the Apollo missions. Every rocky body in the solar system carries a unique isotopic fingerprint, etched during its formation from the distribution of elements in the early solar nebula. Closer to the Sun, certain isotope ratios predominate. Farther out, they shift. The shift is measurable, and it is systematic. The iron isotopes in Earth and Moon rocks both cluster at one end of the range, measured across all known meteorite classes. Thea's contribution to the Earth-Moon system, back-calculated through mass balance, clusters there too. Thea formed in the inner solar system, likely closer to the Sun than Earth. Earth and Thea were not a random encounter between a planet and a wanderer from the outer system. They were neighbours. The composition of a body archives its entire history of formation, including its place of origin, said Thorsten Kleiner, director at the Max Planck Institute and co-author of the study. This finding reshapes the picture of the early solar system more broadly. If Thea formed close to Earth, it suggests the inner solar system was more crowded and more chaotic in its early phases than standard models assume, packed with planet-sized embryos jostling for the same orbital space. Collisions, not anomalies, but a routine feature of the environment. However, the Thea finding also deepens an existing puzzle. If Thea formed close to Earth, its isotopic composition should be similar to Earth's, which would help explain the Moon's Earth-like signature. But the HOP study also notes that while most of Earth's building materials can be linked to known meteorite classes, Thea's composition appears to involve previously unknown materials, a recipe without a clear analogue in our meteorite collection. Thea formed nearby, but it was not made of the same stuff as the meteorites we have. The Moon carries the trace of a body that no longer exists, made of material we cannot directly examine, from a region of the solar system that no longer resembles what it was. But the complications do not end with Thea's origin. On July 9, 2025, Dr. Joshua Snape of the University of Manchester presented findings at the Goldschmidt Conference in Prague, the world's foremost geochemistry conference attended by over 4,000 delegates. The subject was a meteorite, specifically Northwest Africa 16286, a 311-gram rock found on the ground in Africa in 2023, now classified as only the 31st basaltic lunar meteorite officially identified on Earth. Lead isotope analysis dated its formation to approximately 2.35 billion years ago. To understand why this matters, consider the standard timeline. The Moon formed 4.46 billion years ago. Its surface was initially covered in a global magma ocean, a world entirely molten, glowing. That ocean cooled over hundreds of millions of years. Volcanic activity was most intense in the early period. The youngest basaltic samples returned by the Apollo missions, lava flows frozen in time, date to roughly 3 billion years ago. Chinese missions sampling the far side returned basalts at approximately 2.8 billion years. The standard interpretation was that the Moon's volcanic activity was largely finished by around 3 billion years ago. Northwest Africa, 16,286, formed 2.35 billion years ago, nearly a billion years after the Apollo basalts, and more than 600 million years after the models had predicted significant volcanism should have ceased. The age of the sample is especially interesting because it fills an almost billion-year gap in lunar volcanic history, Snape said. Nobody sent a mission to retrieve it. It fell out of the sky, a random fragment of the Moon that happened to be knocked loose by an asteroid impact on the lunar surface, that happened to survive entry into Earth's atmosphere, that happened to land in Africa, that happened to be found in 2023. The Moon was geologically alive far longer than the models said it should be. And then there is the question of what the Moon has been quietly collecting. In December 2025, a team led by graduate student Shubhankar Paramanik and distinguished scientist Eric Blackman at the University of Rochester published a study in Nature Communications, Earth and Environment. They used three-dimensional magnetohydrodynamic simulations to model something that had been assumed for decades to work in reverse. The assumption was that Earth's magnetic field seals the planet. a protective barrier keeping the atmosphere in. The Rochester study found that under present-day conditions, the magnetosphere does something more complicated. Solar wind strips ions from Earth's upper atmosphere. Those ions, instead of being deflected away, can be guided by Earth's own magnetic field lines outward into space. Once per month, as the Moon passes through Earth's magnetic tail, those particles land on the lunar surface and become embedded in the soil. The process has been happening for billions of years. What is in the lunar soil is not just Moon, it is Earth. Particles of nitrogen, water, carbon dioxide, helium, argon, carried by magnetic field lines across 384,400 kilometres of space and deposited, grain by grain, into the regolith. The Moon is an archive of Earth's ancient atmosphere, a record written in soil of what the air above this planet used to be, before life changed it, before oxygen accumulated, before any of the conditions that made the current Earth recognisable came to exist. We have been standing on a library without knowing how to read it. In October 2023, Jenica Greer held a piece of lunar dust and read it atom by atom. The crystal she dated, a single zircon grain, essentially invisible without magnification, formed when the Moon's global magma ocean cooled for the first time, 4.46 billion years ago. It is the oldest known solid ever retrieved from the lunar surface. It predates complex life on Earth by more than 3 billion years. It predates the existence of continents. It predates the oxygen in the air. And it was collected by Harrison Schmitt on December 11, 1972, placed in a sample container, flown back to Earth and filed away in storage for 51 years before the technology existed to read it properly. The Moon is 384,400 kilometres away at its mean distance. Humans have walked on it, 12 of them, between 1969 and 1972. We retrieved 382 kilograms of surface material. We have run thousands of supercomputer simulations modelling its formation. We have measured its isotopic composition across a dozen different element systems. We have tracked its volcanic history through basalt samples and meteorites that fell to Earth on their own. And we still do not have a single model that explains, simultaneously, how it formed, why it looks so much like Earth, why Theia came from where it did, why the Moon was still erupting nearly 1 billion years later than expected, and what exactly those two massive anomalies sitting inside Earth's mantle, possible remnants of Theia itself, as a 2023 simulation suggested, actually are. This is not a failure of science. It is a description of the problem's actual size. The Moon is not, as it sometimes appears from a distance, a simple object. It is the record of a collision between two planets that no longer exist in the forms they had. It carries within it the chemical memory of a body, Theia, that was completely destroyed 4.5 billion years ago. Its soil contains particles of Earth's ancient atmosphere. Its mantle may still hold pieces of the impactor. Its surface bears the age of its cooling in crystals so small they have to be evaporated atom by atom to be read. Every answer we find opens a room we did not know was there. The canonical model persists not because it is right, but because consensus, once built, requires more force to move than the force that built it. The anomalies were always known. The isotope crisis was named a crisis for a reason. The canonical model's defenders did not deny the problems. They noted them, published them, and continued working. That is how science operates when the problem is hard enough. Not with certainty, but with successive anchors, each one more precisely placed than the last. Jenica Greer's crystal is 4.46 billion years old. It is an anchor. The next one will be placed somewhere we have not yet looked. The Moon is not solved. It is the nearest unsolved thing in the sky. If this gave you a new way of looking at the object that has been above you every night of your life, consider subscribing. I want to know, which part of the Moon's origin story surprised you most? The isotope crisis, the Synestia model, or the fact that lunar volcanism was still happening less than 2.5 billion years ago? Let me know in the comments.